In this video, we are going to talk through the definition of a surface integral. So this is the last kind of definite integral that we're going to look at for this semester. All right, so the idea here is that we've got some kind of surface. So maybe the surface of a sphere or paraboloid or whatever kind of surface that we have. And what we want to do is integrate some function over that surface. So we're looking for the total value of that function at all the different points on that surface. Okay, so as with all of our definite integrals, we need to make sure that we start with some region that we're going to integrate over and establish some criteria for that. So we want to start with S being a surface. We don't want that surface to go off to infinity, so we want that surface to be closed and bounded in R3. And we need our function, in this case I've used this capital G here, to be defined at all points on our surface. So all of the points on S are in the domain of our function. Okay, and then as with all of our other definite integrals, there are several key ideas. For surface integrals, some of them are a bit more complicated, but I just want to talk about kind of the basics here, and then we'll dig into the details in a minute. All right, so as with all of them, we're going to partition our region that we're integrating over. So in this case, we're going to partition our surface S. And when we do that, we're going to take little pieces of the surface. So the little pieces of our partition here would be pieces of surface area. So we'll choose a point in each of those elements of the partition, and we would plug those points into our function. And then we want to evaluate some kind of Riemann sum where we have the function outputs times the size of the pieces in our partition. And so you can see up here in the symbols that I have at the top that we are using a lowercase sigma to denote that differential. So we're going to have a delta sigma sub k, that's a lowercase sigma, where that lowercase sigma is going to represent the surface area of each of those little pieces. And then we're going to add all those up and take the limit as the norm of the partition approaches 0. So we need to think a little bit about what we're going to define as the norm of that partition. And provided that limit exists and is the same for all choices of partitions and points, that should be how we would define a surface integral. So an integral over a surface S of a function. Notice this is a function of 3 variables, but it is 2 integral signs. That has to do with the dimension of what we're integrating over. So although the surface, say of a paraboloid, might live in R3, the surface itself is 2-dimensional. When you measure surface area, you measure that in square units. So you've got kind of an up and down and a sort of back and forth way that you can move on that surface. So 2-dimensional surface area. So this should be how we define that. There are some subtleties in the details of a surface integral. Some of that has to do with the fact that the function that we're integrating is a function of 3 variables, and the surface that we're integrating over is really only 2-dimensional. So let's look at some of the details. So the details of surface integrals can be kind of complicated, and how you might actually go through the details of that might have to do with how your surface is represented. So we've talked about that we have several different ways to represent surfaces. An explicit equation where you have z equals f of xy, or x equals f of yz, or y equals f of xz. You might have an implicit equation where you have f of xyz equals a constant and perhaps you can't solve for x, y, or z. Or you might have a parameterization of a surface. So depending on how we are given an equation for the surface or how we prefer to think about representing that surface, we might go through the details of this definition a little bit differently. Our textbook actually goes through this with a parameterization of the surface, so you can look at that in the textbook. I am going to go through this with an explicit surface, since that is the kind of surface you are probably most familiar with. Those are the kind we started with, like, for example, z equals x squared plus y squared. Okay, so what I have drawn over here is a little picture of just some surface represented by z equals f of xy, an explicit representation of an equation for a surface. And then we're going to go through quite a bit of detail here before we really get to the Riemann sum. So again, some of that has to do with the difference between the dimensions of the inputs for our function, the domain of our function, and the dimension of our surface that we're integrating over. All right, we want a smooth surface, so that would mean it's differentiable everywhere, given by z equals f of x, y. And we are going to look at a projection of the surface down into the xy plane. And so just like when we dealt with that for triple integrals, when we looked at the projection of some three-dimensional region down into the xy plane, we denoted that rxy. And your textbook will start using that notation throughout. Really, we could do this definition instead of z equals f of xy projecting into the xy plane. We could set this whole definition up projecting into one of the other coordinate planes. So, since z equals f of xy is a function, since that will be a function, then that means that there are no 2 points on this surface, no 2 xy points that have the same z coordinate. So when I do this projection down into the xy plane, that will be a 1-to-1 projection. So since z equals f of xy is a function, I will have a 1-to-1 projection of my surface S down into the xy plane. That just means that there are no 2 points on my surface that end up projected down to the same point down in the xy plane. I need my function g to be defined for all points x, y, z on S, so that is as we talked about before. And we're going to make some requirements on our surface S so that that projection into the xy plane is connected, closed, and bounded. So closed and bounded are basically just so that our region is not going off to infinity, and so that when I partition, I've got points, including on the boundaries, that can be plugged into the function. Connected means that it's not 2 separate regions. I want them to be connected so that I can move between all points in this region without having to go outside of the region. If it weren't connected, I could just do 2 separate integrals. Now, what you see next here is that we're not actually going to partition our surface. We will end up with a partition of our surface, but we're going to start by partitioning that region R down into the xy plane. So I've drawn a little picture of a rectangle over here down in the xy plane, one of the little rectangles in the partition of R. So this is like we did when we did double integrals. If we use a rectangular partition, then we're going to get this representation that the area of each of those R sub k's is delta x sub k times delta y sub k. So similar to what we did with a double integral. And we're actually going to choose our points xk, yk in that little region down in the xy plane. So I'm going to choose an xy point there, and then I'm going to map that up to my surface so that I have a point xk, yk, f of xk, yk on the surface. So there is my xyz point, xk, yk, zk point that I'm going to choose and plug into my function. All right, so now basically what I need to do is think about how that region down in the xy plane induces a partition of our surface S. Okay, so what I've drawn here is a little bit enlarged picture, our region Rxy down in the xy plane, and I've got my little R sub k rectangle down in the xy plane, and I've projected not only that point up onto the surface where I've got my point xk, yk, f of xk, yk, but I project that whole rectangle up. So all of those boundaries of that rectangle down in the xy plane, I'm going to project up to my surface. And so then I will get this little curved piece on my surface here. That's the projection of that RK onto the surface S. And so in essence, that induces this partition of S. And we've got points chosen in each of those little pieces of that partition. Again, those points really came from my rectangle down in the xy plane, but when I projected that up, I got an xyz coordinate that would be on our surface. All right, but we're not even going to use that. We're actually going to use tiles, essentially. So this t sub k is the projection of my rectangle R onto the tangent plane to the surface at our point. This is why we need a smooth surface, so that we can define a tangent plane at the point. So I've got this plane here labeled T, and that's supposed to represent a tangent plane to the surface at our point xk, yk, zk. And so I'm not only just projecting my rectangle up onto the surface, I'm projecting that rectangle up onto the tangent plane to the surface at that point. And the whole idea is that I can then fairly easily represent the size of those tiles, those little flat pieces on the tangent plane, and use those as approximations for the surface area. Okay, so the norm of our partition here is actually going to be defined as the norm of the partition of R. So that's just like what we did with double integrals. So that was the length of the longest diagonal of all the rectangles in our partition of R. And then we should notice too that as the norm of that partition approaches 0, that tangent plane that I've shaded in gold here is going to become a better and better approximation for the surface area of that little curved surface. So just think about if you're tiling some sort of curved surface with little tiny tiles versus great big tiles. The more small the tiles are, the more they approximate that surface there. Okay, so the area of the little piece of the tangent plane will approach the little piece of the surface area. Okay, and the surface area of our surface S is just the sum of all the pieces of the surface areas. Add it up, take the limit as the norm of the partition approaches 0. And since the size of the tangent plane pieces approximates the size of the surface area pieces, we can write that the surface area of S is equal to the limit as the norm of the partition approaches 0 of the sum of all the tangent plane pieces. And it's not equal to without the limit, but as the norm of that partition approaches 0, remember that those delta t sub k's approach the delta sub k's, and so if that limit exists, then the limit is the same as we get these infinitely small little pieces of tile. Alright, so our next task is to describe the area of that tangent plane tile. The difficulty here is that in general you would expect that tile to be tipped, so it's going to have a different surface area than the area of our rectangle down in the xy plane. Alright, let's talk about how to do that. So here I've got another version of that picture. It says, without loss of generality, we can assume that our point is at the corner of the r sub k rectangle nearest the origin. So I've got a point down here labeled in red, which would be nearest the origin if we had our axes in standard position. And the idea here is that it's just easier to draw when I do this. We could have this at different points in here as well. So if I project up here, I've got sides of this tile given by two vectors. I've drawn these vectors in blue here, and I'm going to label a couple things on the sides here. So the first vector in my picture, A, would be this one that's kind of going to the left and toward you, and B would be going to the right here. So that vector A has a delta x, if I have my axes oriented as usual, down here in the xy plane. The side parallel to the x-axis here would be our delta x. So this vector has a delta x distance in the x direction, in the I component direction, 0 in the j component direction, since we're going parallel to the x-axis, and delta z would be how far up or down that vector goes. And so that gives you the tilt of that little tile that's up on the surface there. Similarly, for the b vector, down in the xy plane, the distance parallel to the y-axis would be your delta y sub k. And so if you look at that vector up there, the horizontal component of that vector parallel to the y-axis would be your delta y, 0 in the x direction, and then the z direction you'd have a delta z sub k. Next thing that we're going to do is use some partial derivatives to approximate average rates of change. And so in this next step here, I have replaced my delta z sub k's with del z del x times delta x and del z del y times delta y. So that comes from the idea that on a small interval, del z del x is approximately equal to delta z over delta x, and you just multiply both sides by delta x, and then similarly for del z del y. Alright, so I've got some vectors, and now we're going to use those vectors to find the area of that little piece of tile. So this goes back to something that we did really early in the semester. The magnitude of the cross product of two vectors gives the area of the parallelogram formed by those two vectors. So here we go. We're going to take the cross product of these two vectors A and B that I have up above. And that will give us the size of that little tile, that little tangent plane piece. All right, so our delta t sub k is equal to the magnitude of the cross product of those two vectors. In this next step here, I've just gone ahead and done the cross product, so I didn't write that out. And then I need to find the magnitude of that cross product. So you can see in the next step here, I've just got magnitude of a vector. So all of the components squared, added up, and inside my radical. All three of those components contain a delta x, delta y, the quantity squared, inside the radical. So if I factor out that delta x, delta y, the quantity squared, then what I'm left with is what we have in this next step. And then in the subsequent step here, I've just represented that delta x, delta y as delta a, sort of a more general representation of that. Okay, so we've now done all the heavy lifting to try to get our surface integral. I've represented the size of the delta t's, and remember that the delta t sub k's approach the delta sigma sub k's as the norm of the partition approaches 0. So we should be able to do our definite integral definition now. Okay, so all of that work we did, together with the fact that the surface area of S is given by this sum of all these little surface areas of these tiles, and then take the limit as the norm of the partition approaches 0. In this next step, I've just replaced the delta t sub k with what we got when we did that cross product of vectors. And that is a Riemann sum. And so provided it converges to that same value for all choices of our partition and points, we get that the surface area is given by this double integral. And so you can see the relationship between the symbols in our Riemann sum and in our double integral. So notice that this surface integral that we started off trying to define ended up being represented as a double integral. We define this integral to be the surface area integral of S and denote it double integral over the surface S of d sigma. So the key here is that when you see that d sigma and recognize that you're doing a surface integral, you're basically going to have to convert that to become a double integral. And the messy part of that is dealing with what the d sigma is. And so for the one we started with, z equals f of xy, your d sigma ends up represented as this magnitude of the cross product of some vectors and then simplified. So I don't usually go through that whole derivation of that. I usually just remember that format so that when I see that d sigma, I know that I can represent it as this square root of a couple partial derivatives squared plus 1 added together, all integrated over my region R as a double integral. All right, so we can similarly define the surface integral of g of some function over S as, again, a surface integral, and then we can rewrite that in terms of a double integral over the region R. So this surface integral that I have written down here, if I project that into the xy plane, then my function g is going to be a function of x and y. If I'm going to be integrating with respect to x and y, then I need my z to be my function of x and y. Remember, that's how we got our point at the beginning. We chose an xy in the xy plane, and we plugged it into the function where z equals f of xy gives the equation of the surface. And then in place of the d sigma, you've got this square root of these partial derivatives squared. Del z del x, the quantity squared, plus del z del y, the quantity squared, plus 1, and then dA. And so you're going to end up integrating over this region in the xy plane that's the projection of your surface down into the xy plane. All right, so it's important that you pay attention to which partial derivatives you're finding and that those are from the equation of the surface. All right, so you can extend this definition to do lots of different kinds depending on how your surface is originally represented. So we started with z equals f of xy, But you can similarly define surface integrals over other kinds of surfaces. If I have a surface S given by y equals f of xz, and I do a projection into the xz plane, so say I have some sort of surface here, and we project back into the xz plane, then my integral would be over my region in the xz plane. And if I'm going to be integrating with respect to x and z, then my g function would need to be all written in terms of x and z. So in place of y, I would substitute what y is equal to for my equation of my surface, f of xz comma z. And then in this case, my tangent planes would be projected into the xz plane. So I'm going to have some partial derivatives here, but they will be partial derivatives of y with respect to x and z from the equation of my surface. So you're going to be looking at partial derivatives of your surface equation with respect to the variables for the plane you're projecting into. And then my dA would be dx dz or dz dx, depending on which order I want to do that integration in. Then if I instead am projecting into the yz plane, so I have some region and I project that back into the yz plane, and so I'm going to integrate over that region yz, then my surface integral of the function would be integrated over ryz. My g function would need to be completely in terms of y and z. So in place of x, any x's that are in the function I'm integrating, I would substitute in what x is from the equation of my surface. And then my surface area differential here is going to have this same structure with some partial derivatives squared added together plus 1 dA. But I need to think about where those partial derivatives come from. Those come from the equation of my surface, and they're going to be partial derivatives taken with respect to whatever variables I'm projecting into, yz. So these will be del x, del y, and del x, del z from the equation of my surface. All right, if I have a surface S with a parameterization given by r of u and v, and our textbook goes through this one, so I'm probably not going to go through this one in as much detail. You can look at that in your textbook. But your r of u and v would need to be a smooth parameterization. That requires that the partial derivative of r with respect to u and the partial derivative of r with respect to v are both continuous, and the magnitude of the cross product of those two partial derivatives. So here I've just used the subscript notation for partial derivatives. So partial derivative of r with respect to u cross partial derivative of r with respect to v is not 0. That ensures that neither of those vectors is the 0 vector, and also that they are not parallel to each other. And then we also would want our parameterization of our surface to have some intervals for u and v. So u maybe goes from a to b, and v maybe goes from c to d. And we want that to be a one-to-one parameterization, so that any one point, u comma v point, gives 1 point on our surface. Then our surface integral of g of x, y, z, d sigma will be rewritten as a double integral, but I'll be integrating over the uv rectangle. So r sub uv here. And we're going to integrate our function instead of x, y, and z. That all needs to be in terms of u and v. So remember, our parameterization of our surface would have x as a function of u and v, y as a function of u and v, and z as a function of u and v. So I'll need to substitute those all into the equation of our surface. And then in the similar way that I took the cross product of two vectors to get my surface area differential, we'll do that for the parameterization as well, but the cross product that we'll take here is r sub u, the partial derivative of r with respect to u, cross the partial derivative of r with respect to v. And then your dA will again be in terms of u's and v's, depending on your intervals and what order you prefer to do that integration in. All right, so this magnitude of cross product here times dA, this is your d sigma, and on all of the surface integrals where we've got the surface area differential, One big deal idea is that you need to remember how to set up that d sigma differential and basically convert this surface integral to a double integral. Alright, so in the next video we'll look at some examples, first with explicit and then with parameterized surfaces.